Okay, so let's look at the second problem in the book where I talked about the constraint-based optimization. This time, let us look at x plus y. Z is equal to x plus y is our curve for which we have to find the critical points such that they lie on x square plus y square is equal to 1. Again, if we want to just look at x plus y, that's a plane like that. And visualizing x square plus y square, this is a circle. And again, as z there is not specified, we can think of it as a infinite cylinder that's moving up and down. And where this cylinder cuts this plane, what is the maxima and minima? Right. Let's again do our regular uh, Lagrange multiplier. Because there is only one constraint, we use one multiplier. Hey, by the way, as long as they're equality constraints, extending it is quite straightforward. Your hx y lambda is equal to x plus y minus lambda times, we looked at it yesterday, x square plus y square minus 1. Not yesterday, in the previous recording. If there were two constraints, let's say x plus y is equal to 8 as the other constraint, lambda 1 times this minus lambda 2 times x plus y minus 8. And then you will have h of x, y, lambda 1, lambda 2. So you do dou h by dou x, dou h by dou y, dou h by dou lambda 1, dou h by dou lambda 2, and solve four simultaneous equations with four variables. It becomes more tedious, but not more difficult. Okay, but let's keep it as one constraint. So again, for gradient, we do three different partial differentiations: dou h by dou x, dou h by dou y, and dou h by dou lambda. Dou lambda anyway will be exactly, it will be the constraint x square plus y square minus 1. That lambda just goes off. Here, dou h by dou x, here it will be 1 plus non plus minus 1 minus 2 lambda x square plus y square. So here it will be more or less symmetric, 1 minus 2 lambda y. So this is one equation, this is the second equation, this is the third equation. We equate all of them to zeros to solve this. But let's look at the first two equations. X lambda is equal to 1 by 2x, or x is equal to 1 by 2 lambda. Let's write it like that. Similarly, y is equal to 1 by 2 lambda. So now I can substitute in x square plus y square minus 1 any of, this lambda to first solve for lambda, right? So 1 by x is equal to 1 by 2 lambda, 1 by 4 lambda square plus 1 by 4 lambda square minus 1 is equal to 0. So this is 1 by 2 lambda square is equal to 0. Sorry, 1 by 2 lambda square is equal to 1. This one goes here. Lambda square is equal to 1 by 2. Lambda is equal to plus or minus 1 by plus or minus lambda is equal to plus or minus 1 by square root of 2. Right? It's just tediously going through the process. There's nothing complicated here. You have three equations. Lambda is equal to 1 by 2x, lambda is equal to 1 by 2y, and x square plus y square minus 1. There is x, y, and lambda, three equations, three unknowns. So just solve them. Now, once I know this is 1 by, I know from lambda x is equal to 1 by 2 lambda. So 1 by 2, so root 2 by 2. So x is equal to 1 by 2 times 1 by root 2. So again, 1 by root 2, right? Or minus 1 by root 2. Same with y. Y is equal to 2 times 1 by root 2 minus 1 by. So that's if now I look at what is my critical point, 1 by root 2. When lambda is equal to 1 by root 2, I'll get 1 by root 2, 1 by root. When lambda is equal to minus 1 by root 2, I'll get minus 1 by root 2 minus 1 by root. Lambda value is plus 1 by root 2 or minus 1 by. Keep that. Now, what is our dou h by dou x? 1 minus 2 lambda x, 1 minus 2 lambda y. So dou h by dou x is equal to 1 minus 2 lambda x. Lambda is, let's take positive. 1 minus 2 lambda y. So 1 minus root 2x, 1 minus root 2. We now know how to compute exactly the same process. Substitute for dou h by dou x, which is 1 minus root 2x, 1 minus root 2y. This is dou h by dou y. And I need to do dou by dou x of both, dou by dou y of both. Dou by dou x of this thing is minus root 2. Dou by dou x of this thing is 0. Dou by this will obviously be 0, and this will be minus root. If I had taken minus 1 by root 2, it would have been plus. So my Hessians are minus root 2, 0, 0, minus root 2, or root 2, 0, 0, root 2. Luckily, I have a diagonal matrix, so I can just watch these. These are eigenvalues. So, hey, these two are minima. So negative. So this point is a maximum. Similarly, these two are positive, and hence this is a minimum. When lambda is 1 by root 2, these are the values that I got. This is a minima. When lambda is minus 1 by root 2, these are the values I got. That's a maximum. So that's what it is.